postdoctoral student in electrical engineering from the KU Leuven in Belgium, and he's doing his PhD in the group of Chris van Hoof and collaborating with the sensors and optics group at IMEC with Andy Lambrechts. And they've been doing a lot of work around spectral imaging, snapshot spectral imaging, all the way integrated on the CMOS image sensor chip. And Thomas has been doing a lot of work around optical issues, basically challenges that imaging optics encounter when you want to do snapshot spectral imaging, at least in the approach that they take, which is a Fabry-Pérot based approach. So with that, I'll let Thomas basically start.
Thank you very much. So I'll start with a simple story. I was looking at some news articles, and I came across something quite disturbing, which was this. That, yeah, imagine that you go to take a salad here in the bar, and that you find like a dead frog in your salad. Now, sometimes there's also a live frog, so it's not a unique experience. But can you find a frog? Like it's very difficult to find. Like here, it's here. Yeah, and here, yeah. Here, this is the frog. But so, like, if we use our eyes, which are like basically RGB, it's very difficult to spot. So, but of course, like, these frogs are not chlorophyll. At least I don't think they are. And these plants, they will be different. So with maybe spectral imaging, you will be able to differentiate that. So, and that's the original spectral imaging. Not really, but spectral imaging started with remote sensing with NASA in the 1970s. So today I will give a talk on like spectral imaging, specifically snapshot spectral imaging. So and what the challenges and typical pitfalls are with that. And then I will focus on one specific pitfall that is the major work in my PhD, which has to do with the Fabry-Pérot filters. So first of all, yeah, I'll just introduce spectral imaging. Many of you know it already probably, but I'll go through it slowly. So spectral imaging can be seen as an evolution of like normal color imaging, where we start like just by monochrome imaging, where you have spatial details, and where RGB imaging, which are made to mimic our human eyes, they can see color, so we can see whether the apple is ripe or not. That's what it was for. And but to go beyond that would mean that you could see small differences, which are averaged out by the RGB filters, so that maybe you can see bruises or small problems with the apple. And so the goal of spectral imaging, or well, there are many buzzwords like hyperspectral imaging, multispectral imaging. I just call it spectral imaging, where you take an image of the scene, so you have the spatial details, but you take it at many different wavelengths. So you have made basically a monochrome image, but that's very specific wavelengths. Or another way to look at it is that for each point in the scene, you have done spectroscopy with that amount of samples. So you can easily compare that instead of like using point spectroscopy, where you have to look at one point at a time. And so in the market, it's somewhere in between spectroscopy and imaging, which is also why it's sometimes called like imaging spectroscopy, where imaging usually has like much higher spatial resolution and speed than the hyperspectral cameras, but of course spectroscopy will have a much higher resolution spectrally than the imaging devices. And there is some trade-off in between to make these kind of cameras possible. There are many different ways you can use a spectral camera. The most obvious one is where you just try to discriminate between different objects. For example, you have here some almond nuts, and you want to detect some foreign material which does not have the usual spectrum, and you want to take them out or detect something else. So just discrimination is the easiest problem. You don't need even a good spectrum for that. You just need a different spectrum for each object. A more advanced application would be where you try to match the spectra you measure with existing libraries. So you can, for example, detect what kind of plastic you're working with, or textiles, for example, which is a lot harder because your spectra needs to be comparable to existing libraries. The third, which is unique to spectral imaging maybe, is that you could physically interpret your data instead of like just 3 averaged out samples, RGB. You get a whole spectrum. For example, you take a point on a leaf, and then you can see the spectrum of that leaf. And so what the people in agriculture are looking at, for example, is this so-called red edge, which can move, or this level can change, and that tells something about the health of that plant. And so in order to be able to see that, of course, these small details, the camera needs to be well calibrated, because else there's no point in using the spectral camera at all. So because of this, spectral imaging will enable many new applications, one of which is very nice in art conservation, where at very specific wavelengths, you can see some defects in the painting, or you can see through the paint to see some details. For example, here you can see some details, and you can scroll basically through the different wavelengths and see what happens. So for example, these features, they disappear and appear at specific wavelengths. And so people use this well, recently there was actually in Belgium, like a few weeks ago, where they discovered, they think, a Da Vinci in Belgium, where they used IMEX spectral cameras to look like what the drawings underneath the paint are, to check whether that's really Da Vinci or not. They're still analyzing it, but they have high hopes. Now, most of these applications, they are in IMEC does not do the applications. It's always in partnership with these applications, which have the expertise of how to interpret the data, of course. One of the interesting applications for current problems is like recycling waste, where maybe like 2 pieces of plastic, they will, for an RGB camera, just like the frog, have the same color. So it's maybe very difficult to differentiate. But PVC has a very specific spectral signature, which you could see with these kind of cameras. Another application which is very popular, this is by a company called Gamaya from Switzerland. And they use the IMEX spectral cameras with drones to fly over like crops and to see whether there's some nutrient or water deficiency. And they basically try to give feedback to the farmer of how to, where to go and how to treat the plants. That's the goal. It's a startup in Switzerland. And this is one more nice medical application where you can see the oxygenation live in an open surgery. So if you look at this spectrum here, like for hemoglobin, oxyhemoglobin, or just hemoglobin, these spectra are, if you would average them out like RGB, they would be very like similar. So even a trained physician like will not be able to see, or I assume like that there is a change in oxygenation in the, for example, here the brain. But these spectral cameras can see, like as you saw here, this is a measurement with the actual snapshot spectral camera. You can see these small differences, and then they can make this map. So what you see here is a brain where they looked for epileptic zones, and then they looked at the relative changes of the 2 spectra, see how it changes. So you can create a map of how the oxygenation changes in time. And it's from a collaboration with the Polytechnique in Canada, Montreal. Then a surprising one is that people from the National Bank, they like to use spectral cameras. Because, believe it or not, I tried it. If you take like a banknote and you put it under the spectral camera, there are actually many features hidden at very specific wavelengths. So if you scroll through them, then you, for example, like half of this, like this house thing, it will disappear at specific wavelengths and appear again. So they are very interested in like making it more difficult to. But of course, if these cameras become affordable, maybe then that won't help. But yeah, we'll see. So the current trend, like big spectral imaging, has been there since the 70s in satellites for remote sensing at NASA. But the current trend is to bring them to industry, where you have many modern like requirements. Where, for example, we want to put them on drones. We want to put them in small satellites, like these called CubeSats, and in more difficult environments. And you want them to be cheap, reliable, robust, as in if I shake them, the components are not like misaligned. So it's robust to use by non-expert users. And you want them to be lightweight, especially if you want to fly with a drone, because battery is really an issue there. And so what IMEC has done, because typically these kind of cameras, they are were at least very bulky, where you had lots of components like prisms, or gratings is of course not bulky, or beam splitters to facilitate the spectral imaging. But IMEC has created a technology where they integrate the spectral sensing element, like the filters, on top of each pixel, and so they can throw away everything and only keep the lens and the sensor. So they can make it very compact. And they do this using a concept called Fabry-Pérot filter. I think many people here are familiar with it. But the Fabry-Pérot filter is a filter, is an etalon, where you take two parallel mirrors, and depending on the distance between the two mirrors, there is a different wavelength that will resonate and be transmitted. So when you tune the distance of the two plates, you can make a filter which transmits a different specific wavelength. And so IMEC can, that's the unique thing about IMEC at the moment, is they can produce Fabry-Pérot filters on a pixel per pixel level. So you could create a sensor which can see many different wavelengths. And so, and this is not a complete filter, this image over here, because I cannot show it. But this is after one process. This is creating a Bragg mirror, like a dielectric mirror, to create two plates, basically. And so what IMEC does, they don't create the sensor. What they do is they get an image wafer, a wafer with image sensors from the manufacturer, and then they put these filters on top of each pixel, and then the wafer is processed basically as usual. So they can create these sensors which look identical to the sensors even if they would not have the filters. But that's how IMEC works. And so of course once you have this flexibility of putting filters on each separate pixel, you can become creative with what kind of layouts, what patterns you will put on the sensor. So of course you could make something like an RGB sensor again, but that would be kind of pointless because there are many good RGB sensors already on the market. But so the typical pattern on an RGB sensor is the RGGB, and then this RGGB is repeated periodically over the sensor. You could extend this idea where you add one more band, for example. So you have an RGB and then near-infrared band, and then you repeat that. So then you have an image sensor which has 4 bands, which is already a multispectral sensor. You could go further, where you have 15, 16. I'll go deeper in that later. Bands where you have like a mosaic of 16 filters that is repeated. Of course, you lose spatial resolution there. If you really want the highest possible spectral resolution using this kind of technology, what you do is, instead of having blocks, you have per row the same, a different filter. Of course, this is not snapshot anymore, because you will require a scanning motion to make sure that each filter, each filter has seen each point in the scene. So this is, you could use this like on a satellite because it moves, or you could like on a conveyor belt or other setups. But today I want to focus only on snapshot spectral cameras because that's the interesting one at the moment. Just to make sure that it's all clear, with a snapshot camera, in spectral imaging, I mean that if I take one shot, like one frame with this camera, then I have acquired the whole data cube. So I would get an image, and for an image at many different wavelengths, or otherwise done spectroscopy for each point in the scene. That's what snapshot is about. And then once you have that, you could create videos, live real-time applications. IMEC has 2 solutions for snapshot spectral imaging. And they differ mainly in the layout of the filters. You have the snapshot mosaic and the snapshot tiled. The snapshot tiled mosaic is, as the name suggests, there is a certain mosaic, like here, a 4x4 pattern, so 16 filters of different wavelengths. And then this pattern, like this block, is repeated periodically over the sensor, just like in the RGB sensor. And then you have basically created a snapshot spectral camera. Of course, the more filters you use, the more spatial resolution you will lose. the sensor stays the same size, so you lose that. Compared to the line scan sensor, there you have high spatial resolution and high spectral resolution, but the trade-off is in the temporal resolution because you cannot do that anymore. But these snapshot cameras can work up to 300 frames per second to create real-time video. And so, because I told you that you have these CMOS image wafers and they are processed as usual after depositing the filters, you can just use the sensor in like the normal cameras that already exist on the market, like here, like Zimea camera. It's very small. It's one of the smallest ones, and it's just in there. And then you have a very compact snapshot spectral camera, and you can, yeah. This is very robust because the filters are monolithically integrated. If you shake it, it won't matter. Okay, maybe the lens. So that's the nice thing about this technology. I mentioned that there's a second way that IMEC does spectral imaging, and that's like the tiled. So where we have like one block of filters, the same filters, and then that block is repeated over and over. No, not repeated. So this is one block, one filter, another filter, another filter, another filter. To do that, to make an image there, of course, you will need a duplication because each block will have to see a copy of the scene. And the disadvantage of that is that you lose here, well, you have extra bulky components because you need the lens array to duplicate the image. But this was mainly done to reduce crosstalk in the sensor. Which brings me to the pitfalls of this kind of technology. Let me check the time first. Okay, perfect. So there are many, I will focus on a few pitfalls that are typical to spectral imaging, but also typical to this kind of technology. And the first one being the fact, yeah, I'll go into that, sorry. Before I go into the pitfalls, I want to say that not all pitfalls are necessarily always a pitfall. They're in principle, they are bad, but depending on your application, you might not care about them. Because if you just want to discriminate between stuff, then no matter how accurate the spectrum is, if the spectra are wrong, but they are different enough, you can still use all applications here. And there are many people who are just interested in classifying stuff like this. If you want to compare it to existing libraries, then of course your spectra need to be well calibrated, the artifacts need to be removed because you want to have something comparable to maybe other kind of hyperspectral cameras. Even more so if you want to do physical interpretation, because then, yeah, you want to be able, if there's small bumps in your spectrum, which are artifacts, this might be misinterpreted by people who are expert in their domain, or they might just not like your system at all. So yeah, the first one is the most obvious one. If you try to increase the spectral resolution, then you need to subdivide the spectrum in finer and finer like bands. But the finer the bands, the less light you will collect, and so you will run into troubles with signal-to-noise ratio easily. One way that IMEC tries to solve this is by going to backside illuminated sensors. Like all the sensors that I've shown you so far, almost all sensors are front-side illuminated, but they are developing backside illuminated sensors to basically solve the problem, accommodate the problem solving of the signal-to-noise ratio. The second one, which is typical to spectral imaging in general, is that you have to accommodate, well, it's also in color imaging, of course, but here more important, so because you don't want to just make nice photos, you want to have something that is physically meaningful often. And so you have to compensate for the ambient light. Because if you have a filter bank, so this is a collection of filters, so this is where you will sample the spectrum. If you have an LED which has only light here, then all these filters will be useless, basically. And you have to make sure that you white balance this non-uniformity. If you have like light bulbs which have like these resonance peaks, then you can run very easily into trouble in your measurements, like you have artifacts in your measurements, or you run into trouble with your dynamic range, because you need you already need lots of like light, but these will saturate while these still don't have enough light. So that's a typical issue you have to take into account when creating a system. This becomes a problem when you are in this very popular application of flying with drones outside over crops, where the sun during the day changes position, the spectrum also kind of changes, and if you have a cloud passing by, then you have your spectrum will change as well on the ground, and it might be only partly illuminated. So part of your image has a cloud and part not, and the cloud moves during time. So these are like real issues that people have in the field with this. Then one of the more important ones for this kind of snapshot technology is crosstalk. It's of course also there in color imaging, but there are two main ways that crosstalk exists. You have the optical crosstalk, where the photon gets to the next pixel before it's converted to an electron, or you have the electrical crosstalk, where the electrons diffuse to the neighboring pixel. I don't have any claims at the moment like which one is the major dominating effect in our sensors. It might be optical because we have a large stack of filters on top of them, so there's lots of possibility for this kind of crosstalk. And so if you characterize the filters, so these are the filter responses of like these 4 pixels, which are 5 pixels, which are near each other. And so you can see that the red one, which is this one, it has these bumps, which is caused by crosstalk. So if you have these bumps, then your spectrum will be, of course, wrong, and you will need some kind of software correction to have a linear combination of all the filter outputs to compensate this. This becomes more difficult when you realize that this crosstalk is angle dependent. So then, depending on where the filter is compared to the optical axis of your lens, you might not predict the crosstalk correctly. So this is an important issue. If there are any people who know lots about modeling crosstalk, please talk to me after the presentation. And so I mentioned that the snapshot tiled was mainly introduced to reduce this kind of crosstalk. You of course still have the crosstalk. Well, you have the lens array which reduces the angle, but you have still crosstalk between the pixels, but it's only just like in color imaging. Well, you have the spatial crosstalk, but you won't spectrally contaminate with other wavelengths your measurements. So that's the main reason that this sensor was introduced. And then there's another like concern with this is that if you go to because we want smaller devices, smaller pixels, high resolution, if you make these kind of filters much smaller, we fear at least that you will get into trouble a lot with diffraction because you have these small apertures here, and then crosstalk will become like unmanageable. So that's a major concern with this technology. This brings me to something that I've been working on personally, which is a pitfall very specific to IMAX technology with the thin film filters. And that is that these thin film filters, they are sensitive to the angle of incidence. So if we have here like a Fabry-Pérot with dielectric mirrors, if you look at it with collimated light at normal incidence, then you have a certain wavelength that is transmittant. You have this transmittance curve. If you tilt the sensor or you change you go to oblique incidence, then what you will see is that this transmittance will just shift towards shorter wavelengths. So you transmit basically another wavelength. If you have a whole cone of light, a range of light, then you have a summation of all these shifted like transmittances. So what you actually get in this case is the sum of all these contributions. So you increase also the filter bandwidth. And so, because eventually you want to make images, and so you use this sensor with a lens. So, and the lens focuses the light on each pixel, like here. And if the pixel with the filter is not on the optical axis, you will have a chief-ray angle, if it's a non-telecentric lens, of course. And then you have a larger incident angle on this filter, and so it will behave differently. Even if this filter is exactly the same as this filter, you will still have a different measurement with this one, because it will sample the spectrum at a different wavelength. And so what you see, this is a simulation where you have the, go stand closer, where this one is the transmittance at normal incidence with collimated light. And then the further away you put this filter from the center, you will see that the filter shifts and becomes wider. So this is what you actually use to sample the spectrum with. So you lose spectral resolution as well. And so in practice, when you are making measurements, this means that, for example, here's a camera of IMEC. If you take a sample, which is, well, no matter how you look at it, like it's a Lambertian surface, basically. Like, no matter how you look at it, it's the same reflectance. And you put it at three different positions. What you expect is to have 3 identical measurements of the spectrum, like the reflectance. But instead, because of this chief ray angle and cone of light, you will get 3 different measurements, where the spectra you measure are shifted, depending on where the object is in the scene. And that would be quite, depending on what kind of application, could be very bad, or you couldn't care because maybe it's not important for these shifts in your application. But imagine like you're looking for a small difference, like a spot on your arm, and it would be, depending on where I put my arm here or here in front of the camera, it would say like cancer or no cancer. That would be a bit silly. So that's the problem we try to solve. And so in practice, what this means is that you are limited in what lenses you can use or cameras you can design with these kind of filters. Because if you want to use like wide angle lenses, they often have like large chief ray angles. And well, you can of course go to telecentric lenses, but they are often more expensive than the equal focal length. And so you'll run into trouble there. Second one is you can also not use very large apertures, like low f numbers, which is important in applications where you have like low light, where you require very fast integration times. So then you run into trouble. So these are limitations on what cameras you can design and what applications you can use. There's another effect which also comes to mess up the things a bit more, which is an effect that is very well known. It's called vignetting, which is probably known to everyone, but I'll repeat it for sure. Is if you look at a uniform scene and you still see a fall off, that's what we call vignetting. And one way that vignetting appears is that because of the finite dimensions of your lenses, that part of the light beam is cut off. So like if this lens would be larger, then you would be able to fill this whole aperture here. But you lose here this part of the light beam for the oblique incidence. So that means that you get less light and there will be an intensity fall off, and that's what you see. In practice, when you are dealing with this problem of angle of incidence, this means that, depending on where your filter is, your exit pupil will change in shape, and so the distribution of incident angles you get will also be different. So this is something you also need to take into account if you want to predict how your system will behave or simulate it. And this is precisely what I've been working on trying to predict how the filters change depending on what lens you use, and to try to make sure that we can expand the available options of lenses and applications where this is a problem. And so what I did is an analytical study, like trying to model this analytically, trying to understand the distribution of incident angles, in this case for an ideal circular aperture, and then calculating how this distribution of incident angles affects the shape of the filter, and from then also calculate where the actual sample was taken, so that you know at which position to plot your data point. And so the main result of this first analysis was this equation, where this lambda is the wavelength at normal incidence at collimated light. This is the one you design it for, basically. where you take into account the chiffre angle and the cone angle, which is the F number basically. And then this formula gives you the actual central wavelength at which your sample was taken. And so this is the position at which you should plot each filter output. And so if you remember this example where I put the same object at 3 different positions and compared the spectra, and in the beginning we got 3 different spectra, but if I now for each data point I know where the actual filter was positioned in the optical plane, then using this formula I can replot each point, and then all the spectra are aligned again. And the same thing I did for vignetting, where you have a model of how this light beam is cut off, basically, and so the distribution of incident angles is limited because of the shape of the exit pupil changes. And similarly, you can then predict how these filters, how your measurement will change, it shifts, and then correct it. So in conclusion there, it means that like using this model-based approach, it is possible to expand the lenses you can use. You can have lenses which have larger chiffre angles, so wide angle lenses. You could use larger apertures, lower F numbers. There's of course a limit because this only corrects the shift. But as you saw, the filters also increase in bandwidth, so you lose spectral resolution. You could in principle try to attempt some deconvolution. I have not done that so far. But with this formula you can only correct the shift, not the spectral resolution. And the nice thing is that you can now go to non-telecentric lenses, which are often cheaper, and that facilitates many more applications. So the goal, well, the question is now when we would be satisfied with our spectral cameras. And I think the answer would be that instead of this kind of article we find in the news, we could find this kind of article so that we can actually find this frog very easily. So thank you. Yeah, sure. Yeah. Can you speak up a bit? Thank you. Yes. Of these filters. Yes, so I think the question is like what is the effective refractive index? I'll go back to the formula so that people know what I'm talking about. You have this formula here. I didn't name it here, but this is a parameter, the effective refractive index, which quantifies how sensitive the filter stack is to the angle of incidence. The smaller, the more sensitive. And so this effective refractive index for the filters that I've been working with is about 1.7. So like for a 15 degree like angle, you would get, I think, a 10 nanometer shift of your spectrum or something like that. So you want anything in specific? The question is about the Bragg mirrors, you mean? Yeah. Like anything in specific you want? Because I cannot tell a lot about the details. I'm not allowed, basically. Yes. Well, no, they actually have all the same, but so it limits the spectral range you have. So in practice, for example, in this, I'll close this and I can easily scroll to the slides. Like if you remember this line scan sensor where they have row per row, then you have much more filters, and if you want to make one which covers the whole range, like from that silicon can from 400 to 1000, then you need 2 separate stacks basically, and so you need to make 2 kind of mirrors. So I think that answers your question. Maybe I elaborate on that. In the mosaic sensor, these mosaic sensors, they currently, at least, they cannot cover the whole 400 to 1000. It's either 400 to 600 or 600 to 900. You can make a dual camera where you have it, but it cannot, because of that, also cover the whole range in one mosaic camera. Yes, thank you.
For the effective index, I mean, that's something that you basically can calculate based on the structure and the
Yes.
materials that are in the fabric.
Exactly. Yes, so the question is like, how do you calculate this effective refractive index? Because yeah, if you don't have this parameter, you cannot apply all this stuff. There are two ways that I see. One is the theoretical way, where you go use, well, there are three ways. One is in the book of Mr. MacLeod, Angus MacLeod. They have a formula for this kind of filters actually, like if you have dielectric mirrors with high and low refractive index filters that are alternated. There's a theoretical formula that gives you the effective refractive index. Another way, the pragmatic way, is you take your sensor, you take a monochromator, and you characterize your sensor, and then you tilt it, and you see how much it shifts, and then you know the effective refractive index as well. Another one is where you use like thin film calculation simulation software. You can also extract it from that, but that's equivalent to basically doing an experiment in real life. Yes. Yeah, sure.
So you're using a CMOS sensor?
Yeah.
So the CMOS sensor has a particular
Exactly.
Spectral sensitivity itself.
Exactly.
So there'll be some filters that you might have a low SNR just because of the sensor?
Yes.
So is that, do you have challenges there and exposure, because you can't have a different exposure duration for every,
So I'll take an.
well, I don't know,
Yeah.
vary exposure duration per pixel or something.
Exactly.
How
So-
does that work?
So this is a bit related to this picture here. So the thing is indeed that like in silicon you have this variation of sensitivity, and you will run into trouble with SNR because some bands will be indeed saturated before, and the other ones still don't have enough signal. And so what currently has been done in, I think it's also been done for Snapshot, where you do HDR to solve it. We take multiple images at different exposure times and then combine the results, so that you have enough signal for all bands. And because you have this high frame rate, you can afford to lose often to take these extra images. I think that's the main solution we have at the moment for that. Yeah. Yes, please.
So currently, I mean, the products that Amic is selling, or the test beds or whatever it is that you're providing, are these based on telecentric lenses? Are these based on low vertical aperture lenses? I mean, I'm trying to figure out where is this in the process of being implemented?
Also,
On the cameras.
so what is like the
Some of the things that you basically
my work, you mean?
some of the analysis.
So yeah, currently well.
Calibrate systems.
Yeah. So currently, this systems are they are being sold. It's commercially available, like a price range. It's also like depending on like how small you want your sensor. It's from $1, basically €1, to 10K, typically for these mosaic sensors. And they are sold mainly with non-telecentric lenses. Although IMEC, of course, recommends using telecentric lenses, but it's often too expensive for many applications. And what they do recommend is only use an F number of 2.8, don't go lower. But of course now this work has been done, we can predict how far we can open the aperture without running into troubles. And so it's currently been in the stage of being implemented in the software that IMEC distributes to the clients. It's already used to analyze some problems for clients, but it's not distributed widely at the moment. But it could open, well, it makes it more flexible to design cameras for applications. Yes.
So we have cold water, cold sodas, cheese, and other things to eat back here. And so you'll hang around for a bit?
Yeah, sure.
I'm sure we have a lot of questions. I know I do. And thank you all for coming. And by the way, one last comment. We're putting together the program for next fall. So if you have suggestions of speakers, I really appreciate that Peter brought the speaker in today. And if you have suggestions and you put me in contact with other speakers, I'd be really grateful for that. So thank you very much, and thank you for.
Thank you.